contribution, as John Womersley was talking about today, the UK contribution to ESS.
Hello, thanks Dan. So as Dan said, I'm Paul Aden. I work within technology. I'm a mechanical engineer and project manager, and I'll be looking after some of the work packages within the STFC's contribution for the ESS. So what is the ESS? To give a little bit of background, in 2014, the UK government set aside £165 million for a spallation source in Lund, which is in Sweden, which is just over here, as you can see. And this is what they're planning on building in total. This is just a nice, obviously pretty image at the moment. It's actually just a hole in the ground. I think they only started pouring concrete a couple of months back. So as it stands, this doesn't exist, but it will do. In the background here, we can see this is Lund and Malmo, and then there's a big bridge that goes to Copenhagen. It's all very nice. Now, when I first took on the project, one of the first things that I sat down and thought was, what is going inside this building? What are they putting in there? So I went straight to the conceptual design report, where I found this. So this I believe was drawn by one of the children of the lead authors, or well, I mean I hope it was drawn by one of the children of the lead authors. But I mean, it's fundamentally all there. We've got the source, and then we've got the cryo section. This is the linear accelerator, and then at the end, the target, and neutrinos and neutrons being scattered off the target to the instrument stations. So if we tidy that up a bit, we get something which looks pretty much the same. So this is a basic schematic of what the ESS is. It's a 600-meter proton accelerator, which accelerates the protons to 2 GeV, where they hit a helium-cooled tungsten target, and then neutrons are scattered off and fed around into various different instruments which sit around it, and they allow scientists to do different types of research. So here's some numbers. I mean, the takeaway really from this is that this is the world's most powerful proton linear accelerator, and also that they want to turn beam on sort of towards the end of 2019. And as I mentioned, at the moment they've just got a big hole in the ground. So building something like that on this timescale is obviously going to cost a lot of money, and as you can see, it does. The total construction costs, as it stands, are around 1.9 billion euros. And then, as I mentioned, the STFC, well, the UK government through the STFC, have put in 165 million pounds, which actually makes the UK one of the leading contributors with regards to in-kind contributions. I think 60 to 70% of this accelerator is in-kind contributions, so we're definitely up there. Now, a lot of the work that is going to go on at the ESS, of that money, isn't all here, but a large proportion of it is. Nearly 50 million pounds at least will be coming here to be spent on, in particular, these two work packages: the superconducting RF cavities and the beam transport modules. So I'm looking after this section. I didn't know anything about this section up until a couple of weeks back, so I apologise if I've got it wrong, but these are the main packages that we'll be doing here. They're not the only packages that are happening. There's still discussions for other things, diagnostics, choppers, RF systems, and things like this. And also there's packages that have already been delivered from that UK in-kind contribution. So this team of beautiful people here, as managed by Keith, who's at the back over there, delivered earlier in this year £1 million package to set the vacuum lab up with various different systems. So we've got a system that allows for replicating any part of the vacuum within the accelerator, another system for testing gauges, and then here we've got a material characterization system, which is an outgassing system, which looks at what you can put in the accelerator and what's acceptable, and then squeezed into just a size of a little bit bigger than a phone box is 10 guys there inside the entrance to the clean room. So back to this schematic. This is a little bit of a breakdown now of how the protons are accelerated. So they start at the source and they're accelerated through this superconducting section. And this section is broken down into two subsections, the medium beta and the high beta section. You can see that of this superconducting section, we're going from 216 mega electron volts to 2000, so it's about 97% of the acceleration through the accelerator comes from this superconducting section. And it's this high beta set package that STFC are going to be contributing towards. In total, there are 22 complete modules. Now, that's what a complete superconducting RF module looks like. It's actually this section here that we'll be looking at procuring, testing, and delivering to ESS. Each one of these superconducting sections comprises of 4 of these dressed cavities. So that means that in total we'll be shipping around 84 dressed cavities to Lund. So inside those dressed cavities are these 5-cell niobium cavities. So I apologize if I'm dumbing down the science a bit here, and maybe I don't understand it, but there's an RF electromagnetic field applied to the cavity, and as that's applied, a resonant field builds up within the cavity, and when a proton arrives at the entrance, providing it's within the right time phase, then it sees constant acceleration across the length, and that's how we get to these high energies. So, in order to do that, though, the cavity needs to be superconducting, and in order to achieve that, it needs to be cooled down to around 4 Kelvin. So that means that we need to apply helium to liquid helium to get it down to that level. So just out on the outside, I've just sort of taken it out. This is the helium jacket that it sits in. So this blue thing here, that's the helium jacket, and then just to the right, you can see it once it's had that jacket removed. So because we're at superconducting in levels, and because we've got this helium sloshing around in there, that means that we need to keep a very low particulate level to prevent any sort of damage or quenching on the systems. And that's why these systems are important, because once we ship other items to the ESS and from all the other in-kind contributions they're getting diagnostics from or whatever they're getting, they need to make sure that it will all work within the systems. So this is what we'll be looking at procuring. There'll be 84 of them. It's a fully dressed 5-cell cavity, and potential for 4 spare. I think that's still under discussion, but I'm not too sure. And these things, this actually exists, as John mentioned earlier this morning. The STFC didn't quite get in on a lot of the design work, so all of the design of this, or a large proportion of it anyway, has already been done. So these are prototypes produced at CEA Saclay. These are dressed cavities ready to be tested. Now, once we've procured the cavities and we need to get them tested, we plan on testing them here inside a vertical test facility. We've already got one on site, which we've been working on in collaboration with Shakespeare Engineering. However, it's not quite the right size and shape for some of the cavities that we're going to be working with. So this is a conceptual design for upgrade or new test facility in order to be able to test these cavities. So this is a slightly novel design in that previously when cavities have been tested, they're sort of just strung down and then dumped in not dumped in a helium bath, but placed in a helium bath. Whereas here, although the test itself the test facility itself is vertical, the cavities dressed cavities are horizontal. So they're already in the same orientation that they'll be used in, so it's a more accurate test. And also they're using the helium jackets which they come shipped in, so that means that less helium will need to be used. So just to sum up the scope of the cavities, really, 84 of these dressed cavities will be going out, plus with a possible 4 spare. in order to make sure that the testing and quality control is done appropriately, we need to make sure we've developed appropriate tests and performed appropriate trials. We'll be looking at upgrading our current verticals test system with maybe new cryogenics and new RF to match that of the SRF. I think the current one is 200 megahertz, and the ESS superconducting RF section that we're looking at operates at 704. So these cavities as well, the RF field applied across them will be around 22.9 megavolts per meter. So again, I'm not fully understanding of this, but the quality factor needs to be better than 5 times 10 to the minus 9. And then once these have been procured, tested, put through all the clean rooms, and made sure that they're suitable for delivery to ESS, they'll actually go to Saclay, where they'll be integrated onto the larger modules 4 in a string that I showed earlier. This is the timeline for that. You can see it's running from around about now up until 2020. So there's a lot of activity going on there, with a total cost of approximately £35 million. Of that, however, £8 million is just for the raw cost of the niobium, which will be used inside those cavities. And this will be bringing about 30 full-time equivalent staff years to the lab here. Now, the other section, the other work package that we're looking at is the beam transport modules. They look a little bit like this. This is one of them. There are actually 10 different types. So obviously I don't want to put them all up, but this is our current prototype design that we have. These modules will be scattered throughout the machine, so they won't just sit in any particular section, but they'll sit in various different locations along the machine. But because they do sit in some of these superconducting sections, in between the superconducting modules I've just mentioned, that means that they still need to be cleaned and have the particulate level measured to make sure that the particulates are low enough to allow them to sit in between those modules without damaging the superconducting modules themselves. So, as you can see, a lot of you are probably very familiar with Vela and Clara, and we've also got Eli in build over in the ETC. These are very similar in design girders. We've tried and tested, and they work, and we're happy with them. And we've gone for a similar approach with these modules. So, although the basic parameters of the module have been set out by the accelerator physics, there's still a lot of mechanical design work to be done here. We need to make sure that the vibrations are taken into effect from the ground to make sure we're not vibrating the magnets too much with the ground floor noise, and also to make sure that the temperature sensitivity of the girder doesn't change outside of the scope of what we can allow. So they're made up of a diagnostic section, a steeromagnet, and some focusing magnets. Now, without the superconducting sections, you can't accelerate the protons. But without these sections, although they look a little bit duller, you can't steer the beam into the further accelerating sections or onto the target, and you can't diagnose it. You can't look at it as it goes down the line to make sure that it's the right shape and the right size and the right energy and whatnot. So again, there's just another image of the prototype that we've got going on. You can see we've got some pedestals, we've got semi-kinematic adjusters on the girder. There's an aluminium slotted girder which allows for adjustment along the beam axis, and there's smaller plates in here which allow for adjustment across the beam axis. And the whole assembly needs to be surveyed and aligned to within 50 microns. And this is the difficult bit, that chamber there needs to be particulate free to sort of ISO 5 or better. So just to quickly go through the scope of that project, we've got two prototypes which are almost ready to be put into build. We've got our final design review in November, and once we've gone through that, we'll be ready to start building those. We've got 3 test chambers to be built, and then we've got 75 of these modules to build, and then another 52 modules without magnets to build as well. And 2 differential pumping systems, which I've not mentioned, and I don't think I'll have time to, but they sit here and here, and they just allow for the vacuum on one side to be much lower than the vacuum on the other side. I think the gradient's about 100 to 1 across that differential pumping section. So that's 134 modules in total, and that cost estimate is around £10.5 million. So the timelines for that are similar to that of the superconducting RF work. We're currently working on prototypes, and then from the end of next year to the end of 2019, we'll be delivering beam transport modules and assembling them on site. So that includes the beam pipe modules, which are magnetless, and the LWUs, which have got magnets on them. On top of that, we've also got the installation clean rooms and the 2 differential pumping systems to ship within that time scale. Now, that's a simplified version of this, which is what I'd look at on a more regular basis, but you get the picture. Now, because there's so many modules, it means that we're looking at having 1 chamber in a clean room being cleaned out and particulate tested every single week for over 2 years. That's quite a lot of tedious work for somebody, so I apologize in advance for that. And again, similar to the SRF, this is going to be around 30 full-time staff equivalent years over that 5-year period. So how are we going to do this, or where are we going to do it? Just across the road. So the building behind this is this building. This is the Engineering Technology Centre. I know a lot of you work there, so we'll be very familiar with it, but for those who don't, this is what we have. There's a couple of soft wall clean rooms, ISO 4 clean room, inside an ISO 5 clean room, a large assembly area with an overhead crane, which is ideal for these large modules, and also vacuum lab for processing all the vacuum work, making sure everything's UHV clean, making sure everything is suitable for moving to the next stage, which will be into the clean rooms. Now, even though that we do have a large set of facilities here, because of the volume of modules that needs to be shipped on both of these work packages, means we'll be doing some upgrades. So this is opposite the Vela control room, and it looks like we'll be doing adding some clean rooms and also a test facility. So the main challenges to do this are going to be the particulate control, obviously cryogenic dress cavities. The sheer volume of units is going to be a lot. Managing this amount of work over this period of time is going to be difficult. And it's going to put pressure on UK industry. There's going to be around 230 vacuum vessels out for manufacture between the mid next year and the end of 2020. That's quite a lot of pressure to be putting down on UK industry. So the tight timescales are going to be another big challenge here. The ESS want to turn their beam on in 2019, and a proportion of this work is on that critical path in order to get that beam turned on. And in order to meet that, we need to make sure that we get the ball rolling as soon as we can. This is only realistically, just less than 3 years away if we don't start soon. But then again, long time scales. So on the other side of that, this is a commitment for a 5-year project. So it's a long time scale from the point of view of some of the other work, at least I've worked on while we've been here. I know that the facilities are here much longer period, but the actual build process for this is 5 years. And in order to achieve this, we need to make sure that we've got strong coordination with a lot of our international collaborators. Although the in-kind contribution will predominantly be spent here, there is mechanical interfaces, there is design difficulties between different components that need to fit in different places. BPMs, for instance, are being done at DAISY, and they need to make sure that they fit inside some of the LWU units. So, we've got to make sure that we collaborate well with our international partners. And we have to make sure that we manage the quality control properly. So, good quality control and good project management are critical for success in delivering all of these units on time. So these are two big work packages. There's 134 beam transport modules, 84 dressed and test cavities. That means that the STFC will be responsible for almost 50% of the ESS beam line. That's quite a large responsibility on the STFC. So we need to make sure we get it right. As I mentioned, some of the beam transport modules are on the critical path to being able to turn this beam on. And the total cost of both of these projects comes in at around £50 million, bringing in around 60 full-time equivalent staff years over the next 5-year period. So we'll be busy. That's all I've got. I don't know. I've no idea. All right, thanks.
Any questions? Paul?
What happens if you don't deliver on time?
I get shouted at. Well, that's obviously a difficulty, isn't it? We need to make sure that that's managed appropriately so that we can see where we're going to. But if we don't deliver on time, then this beam on date will slip. At the end of the day, if there's the units are required to turn the beam on and we don't deliver them, there'll be the beam won't be able to be turned on. So that's big pressure on us, and also reputation damage for the STFC if we don't do it on time. So we sort of have to do it on time. The superconducting RF modules are delivered a little bit later than that. So that means that some of these beam transport modules, the ones without magnets, actually fit in sections where the superconducting RF modules will sit once they're ready. So the pressure for that is slightly less, as I understand, with regards to making sure that we can hit that beam on date. But with the beam transport modules, it's not. So we have to.
But it does seem, from, you said, a hole in the ground to beam on in 4 years?
Oh yeah, sure. I'm not convinced, but that doesn't mean that
realistic timescale.
I would agree, but that doesn't mean I should manage our section of the project to not hit that timescale. Just because to go from where they are to turn the beam on in a couple of years based on working with them, I'm not sure whether that will happen. But we'll keep our fingers crossed, I suppose. But like I said, it doesn't mean that we shouldn't try and hit that timescale.
Sorry, I might have missed a bit. The RF cavities you're talking about, you say that they had actually been designed in Stackley, is that right?
Yes, so I think the cavities themselves and the jackets, so pretty much, let me just go back. Yeah, so pretty much all of this, I believe, I don't know if Phil is here to correct me, no, but I believe they were designed in joint by the team at ESS and the team at Stackley.
Did you then say that they had actually been designed at a lower frequency than you were going to make them?
No, sorry. So this test system we have here is an ongoing R&D collaboration which we've been doing with Shakespeare here in order to get UK industry superconducting cavity capabilities. But this system is a slightly lower frequency. So I think this is 200 megahertz, I'm not too sure, but the ESS will be operating at 704. So our current facility has allowed us to be able to bid and win this work, but it does need some upgrades before we can use it to test the ESS cavity.
Any other?
So for your vertical horizontal test, it's going to be called a horizontal or vertical test. It doesn't look like a very large supply of helium you've got. How many hours of operation do you get out of that?
I don't know. So what I would say is that it's about 50 litres of helium are required for these. I believe the idea is for them to be able to test one cavity a week. So I'm assuming that they would therefore be able to need to top it up. I don't know if Tom might be able to help me with that. 2 weeks?
So 3 cavities, We'll be testing 3 cavities every 2 weeks.
There you go.
Yeah, but is there enough helium to do that?
Yeah, though we'll have helium only in the rest vessel, so they will not be dipped in the bath.
Yeah, so the helium only sits in, so the helium only sits inside this jacket. Yeah, so you'll only be filling.
Yeah, that's a slightly unconventional approach we are taking.
You'll only be filling this section here, rather than all of that. Makes sense. Yes. Thank you.
Okay, Roger.
Is this just an STFC show, or is there some university involvement through Cockcroft?
So these particular projects, I don't know about the SRF work. I think it's just the STFC and ASTEF. The beam transport modules definitely is, and the SRF the same.
Yeah, I think, to my knowledge, there is no real R&D involved in it. But most of the basic R&D and the prototyping has been done at Sackley. So we are actually really just building things, and testing will be the quality control. That's where we are taking the responsibility.
Okay, thank you.
Any other questions with that? Okay, thank you. So, yeah, 20-minute tea break. This has been brought to you by IOP, part of the Accelerators of Ease Group. If you've not already wanted to know about this technician training, go and see him.